So I give you James Allen.
Great. Well, thank you. Hope I can live up to the introduction. Good. So, yes, so today I'm going to want to take a big picture look at the whole issue of conversational agents and especially the area that I have been looking at and thinking about for a long time, which is dialogue really as driven by models of collaborative problem solving. Just as background, we can see these days that conversational agents have arrived. You look at every major mobile OS, and they all have conversational agents, albeit their abilities are conversationally rather limited. You can get it to do things. You can't really have a conversation, like a human-level conversation or anything close to it. And there's an explosion of research that's creating more and more robust systems and more tasks. But what I'm going to argue today is that the underlying representations of these systems is inherently limited. And if we want to move more towards human-like capabilities in our conversational systems, we have to look beyond that. So that's where I'm going to go today. Just a couple of slides. The kind of underlying technology for most spoken dialogue systems or spoken language systems you see today, probably the most predominant and most annoying are all the finite state machines that you talk to when you use the telephone these days and try to call people up. And everybody universally hates them because you're not really having a conversation. You're just saying a few words that you have to know by rote in order to know what to say. And you have no control over the conversation. Much more promising, and where the bulk of a lot of the research in dialogue systems is today, are on frame slot-based systems, where you represent a task by a set of slots with patterns in the language that you can go and extract the values of those slots. And basically, you have an extraction process on an utterance coming in. You extract out the relevant information, fill in the slots, look at what other information you need, which might prompt a successive conversation, a question or something. And this is a very flexible model and can do a lot of different simple tasks. And in fact, it's kind of embodied in this dialogue state tracking challenge, is essentially using these kind of representations. And so many researchers are, as soon as you have a challenge, a lot of researchers get out and try and outcompete each other. But there are many limitations of this model. One is that you generally can do only one task at a time, or possibly there is work where you can interleave and do several tasks, go back and forth. But essentially, you're doing one thing at a time. And the tasks are extremely simple. They're sort of one-shot things. Give me all this information, and I can give you this. And now we're done. You know, I clean the slate, and we start up again with something unconnected to whatever happened. So all of these... But no matter, even if we have these generalizations here, the interaction that the tasks you can perform are very simple, and they have to be predefined. And that's what you can do. You can execute tasks. And the fact that one is using, deep learning and machine learning systems on these doesn't change that fact. Okay? It might make it run better. It doesn't make a task more complicated that you can handle. Okay, so today's talk, I'm saying, can we move towards much more general but practical models of conversational agents, and how might we do that? I should say there's no shortage of good theories on how we might do this. All the way back to the times when I graduated with my thesis, there's a flurry of work on the theoretical foundations of conversation, speech act theory, plan-based speech acts, relation of discourse structure, shared plans by Gross and Seidner, logic of national interaction by Cohen and Levesque, discourse obligations and grounding. There's lots of work out there. but they haven't led to robust practical systems. And so I've been spending, I don't know, the last 20 years trying to say, well, how do we make practical, robust systems that can get the level of generality that we can kind of describe with these theoretical models? And so that's what I'm going to talk about today. So I'm actually going to take a kind of chronological perspective, and I'm going to go through work we've done over the last 20 years to illustrate the various points along the way. So that's the plan for the talk. Okay, so a couple of observations before we start. Most, and I would say, of conversations are actually that we have, people have, are not about performing simple tasks. Even the kind of conversations we might want to have with a computer are not just about executing tasks. There's many different things that you might do. And we're going to look at these various different applications today because these are the areas I've been trying to work in and generalize to. The first ones are actually you want to actually interact with the system to plan and solve problems and coordinate their activity towards solution. So you might not be doing a task, you might be constructing a task. Another one is that dialogues where the system might learn new tasks from the user, from the conversation itself. So the user could instruct the system on how to do something, and now the system can do it for them. Or the reverse, where the user's learning how to do something from the computer. And then there are the essentially dialogues that help a person manage complex situations, like emergency management or something. You've got a hurricane coming through, there's total chaos. How do we manage it? And the way humans manage it these days is from the seat of the pants. They have very little idea what's going on, and they just quickly make decisions and have heuristics on how to do it. There's no overall idea of what's really going on. So that's an area where machines could make a big difference, but they don't very well right now. So that's so these are all things we'd want in an intelligent system, but none of them are actually involving task execution. The second thing is, especially in relation to this conference, language is situated, and intention recognition using that situation is critical. So here's a simple, this is when I was a graduate student, we collected dialogues. In those days, you didn't have to get human subjects approval, and you could go and just record people talking out in wild or in grocery stores. And here's a simple conversation. Customer walks up to the clerk who's stacking stuff on the aisles, and the customer says, "Black beans?" And the clerk says, "Aisle 3. And then the customer goes off. So there's a very simple conversation, okay? What happened? Well, a lot happened in just very few words. And note, they're not even complete sentences. But what happened was, clearly in this situation, what kind of things do customer clerk things, what do you ask clerks about? Well, one of the most common things is where things are. And so when the customer comes up and asks black beans, the clerk says, oh, they probably want to know where they are. That's almost the only thing I can think about why black beans are relevant to us in this situation. And so I can give the answer for that. And if you were building an automated agent sitting in a grocery store, you could, of course, encode all these assumptions in there, and you could, if you had some data, you could do some machine learning, and you could handle this problem, this interaction, no problem. But you didn't. If you do that, you've built a system that works in your grocery store, but it doesn't help us with anything else, right? Because there's no general model behind it. We just learned some exchange for this one application. So if we move to a more complex situation, like we're in a home environment, okay, now you're talking to your spouse. There's many ways this conversation might unfold. You might say black beans as you walk into with the groceries or something, and you say, "Oh, sorry, I forgot to get them." Okay? Or when you're cooking, the spouse says black beans, and you say, "Yes, they're in the cupboard. They're looking for them." Or also when cooking, and you're adding black beans to the pot, and the spouse says black beans, and you say, "Oh, don't you like them?" Or we're exploring nutrition options while you're planning your dinner, and the spouse says black beans, and you say 227 calories in a cup. These are all perfectly good conversations, and they all make sense. Nobody has to think hard about them. And as you can see, there's nothing in the sentence black beans, those two words, that tells you which one of these it is, okay? This is all to do with the situation that you're in if you're going to carry on this conversation. So that's the other main point. To understand and respond appropriately, we need to understand why someone is speaking to us. In other words, what their intentions are. Okay, so that's sort of all the preliminaries. So the task we have at hand is we've got an intelligent assistant on one hand, we have a user on the other hand. We want them to work together to solve problems. What's this box in the middle? So we have natural language interaction coming from the users. We have intention recognition, reasoning, and acting, and other kind of intelligent agent-like things on the other side. So what kind of things do we do in a conversation? Well, we agree on goals. We jointly develop solutions. We identify and resolve obstacles on what we're talking about. We evaluate progress. How are we doing towards our goals? We jointly perform actions. You do this, I'll do that. We learn as needed. These are all things, and they all happen interleaved in conversations. We switch between it as needed in order to get a task done. And as you can see from this little graphic here, we have those four pieces. That shape won't stay there unless everybody holds it up together, right? So this is something that can't be done by a single agent. It has to be done by all of them working together and coordinating their activity. And the central premise of our work is that all human-machine language-based communication can be modeled effectively as collaborative problem solving. Now, there are many conversations that humans have with each other that aren't necessarily so much problem-solving oriented, unless they're at a meta level or something. You might want to get to know someone better or something. And then the goal is sort of to develop that relationship, conversations about other things in order to get that secondary goal. But when we're talking to computers, we're generally trying to get something from them, much more concrete. So, one of the key ideas here is that if we're accounting for conversation, we actually have to look at what's happening at the collaborative problem-solving level, not just what we're doing in the task. And here's an actual dialogue that I had. I partook in this about 10 years ago, back in the days when we actually still sent letters with stamps on them. Boy, that seems like a long time ago now, doesn't it? And so I needed to send a letter to Mexico, and I was at work, and I went into the main office, and I asked, do you know what the first-class postage to Mexico is? And the secretary said, no, which at the time, I must report, I thought was rather uncooperative. So anyway, but I persisted, and I said, well, how do I find out? Thinking I have to make this goal more explicit. And she says, well, do you really want to know, or do you just want to mail a letter? And I say, well, I want to mail a letter. And she said, well, no problem. We'll put this charge slip on it, and the post office will figure it out. So there we got a problem solved. Now note, this conversation has almost nothing to do with the task of mailing a letter. Okay, it does a little bit, but that's not what's... You can't explain the interaction by a model of mailing a letter, you put a stamp on, and you put it in a mailbox, or whatever the task would be. Okay, so what we have is an analysis here. You can look at it at the collaborative problem-solving level. So I can look and say, what's the first task doing? It's introducing a goal, which is knowing the cost of postage and possibly mailing a letter with a little intention recognition. And then when I get to the how do I find out, I'm asking further, I'm trying to tell me how to achieve this goal. So I'm requesting that you identify a plan towards this goal. The next utterance is a request to clarify what the goal is, okay? So here, come back and say, do you really want to know, or do you just want to mail a letter? And at this stage, I clarify the goal. And at that stage, the solution is introduced. Okay, so this dialogue is accounted for very nicely if you think at the collaborative problem-solving level. What's happening with goals, solutions, problems? That's sort of the domain that we're talking about. Okay, so let's move on and say, how do we do this? Well, I'm just going to give a few examples of systems we've built over the years because they illustrate the points quite well. The first one is the namesake system of the TRIPS system. This is 20 years ago, believe it or not. I can't believe it. But anyway, in this case, there's an island, which we have a simulated world for we can reason about. The idea is there are things like hurricanes coming in a certain number of hours, like 10 hours, say. And we need to evacuate the island. We need to find out where all the people are, what trucks and other helicopters or whatever else we have, and how can we get everybody over to the port of Delta, which is over on your right-hand side, and then we're going to get them off in a boat. So that's the task that a user's given. They're sat down in front of the screen like this, and they're just saying, talk to the system and solve a problem. So here, the system's helping the user build a plan. We've got user initiative driven by the problem-solving model, and the result is an evacuation plan. The most common actions performed in this task are adding goals and sub-goals, adding actions to achieve goals, modifying goals and actions, requesting evaluation along some dimension, and comparing options. Okay? This is what people do when they're trying to solve these kind of problems. And I'm going to show you just a 1-minute little clip from the middle of one of these dialogues when there's been a little bit of dialogue so far on finding out where the people are, what resources are available, and we move into the...
To get the people from Calypso to Delta.
All right.
So that's a timeline of the plan.
How long will that take?
It will take 6 hours and 14 minutes.
What if we went along the coast instead?
That option would take 8 hours and 12 minutes under normal conditions.
Forget it.
Okay.
Use the other truck to get the people from Exodus to Delta.
Okay.
Let's use the helicopter instead.
Fine.
Okay, that's a little clip. That's 20-year-old technology, right? You notice he had to speak rather clearly in order to get the speech recognition right. And the synthesis is a little, you can do a lot better these days, but still. So what happened there? Well, let's look at it. Use a truck to get the people from Calypso to Delta. That's introducing a goal. In response, the system plans a route to achieve this goal. It displays it and the time schedule. Person asks, how long will it take? That's requesting an evaluation. The person actually at this time just looks up the data because it's already computed the times and takes 6 hours and 14 minutes. What if we go along the coast instead? That's a complicated one. We're proposing an alternative solution, okay? And by adding an additional constraint on what the plan would be, the system goes through, creates a new route, holds onto the old one, and then actually displays both of them and compares them and says, it'll be, I forget what it said now. It'll be slower, basically. Person says, forget it. That's dropping an alternative, right? The one we were just talking about. Not forgetting the first plan, the immediate one we were talking about. Use the other truck to get the people from Exodus to Delta. This is introducing a goal again. It turns out the route's too long. It's going to be, you've got 10 hours to do it. This is going to take, like 15 hours to get the people off by truck. So we use the helicopter instead. That's a modified goal. Note, you can't just take the helicopter and plug it in as a parameter in the plan now as the truck was, because the truck could actually make one trip out and bring all the people back. The helicopter has to make many hops back and forth. So we have to replan the whole thing. What changed here was the goal, and then we replan. Okay, so how did this work? This was a fairly simple conversational agent, rule-based. It basically had 3 main steps at the beginning. We match into the actual speech act coming in. So there's a lot of full parsing and surface intention recognition. We end up with a speech act and what was said. We match to that, and when we get a certain speech act pattern, we then do context and validation in the discourse context. So is what moves are allowable right now. At that point, we have a hypothesis. We then go to the problem solving and say, is this a reasonable thing to be doing now in the problem solving? And if it says yes back, we can then say, okay, that's what it was. So this allows us, the language interpretation system, to interact back and forth with the problem solving system. So here's a simple example. Say the user says, I want to buy a truck. Okay? The discourse would say, is proposing a goal appropriate this minute? Okay? Now, if it's the beginning of a conversation, that's exactly the kind of thing you'd expect, or something like that. So it would say yes. And then you would say, ask a planner to evaluate, is buying a truck a reasonable goal to have in this domain? And say the problem solver says, yes, good. And so then it would say, okay, we're committing to the goal of buying a truck. And we're updating we're giving a user and a confirmation. We're updating any displays we have. And now the system and the user have a shared goal to buy a truck. It's basically how it works. So we have the speech act interpretation. It's hypothesis testing. That's basically how we interact with problem solving. Although not all rules are problem solving, you can have the rules encode things like greetings and closings and other things like that. And but intention recognition is used to critically as we go along. And here's an example of how intention recognition works. Okay, here's a particular context. Again, you can't interpret these sentences out of context. Okay, the context is we're trying to evacuate the island. The current sub-goal is we're trying to get the people from Abyss to Delta, and we have a plan to move the people by truck to Delta. And you can see that's displayed, the routes displayed on the plan. So this is the context. Okay, the utterance comes in and says, can we use a helicopter to get the people at Abyss? Okay, so you might say, well, what's going on there? Well, the reasoning we might say is, well, the existing plan already moves people from Abyss to Delta. Thus, this is not a plausible new goal, because we've already had that goal and we have a solution for it. So it's not a new goal. What other thing could it be? Well, the conclusion we'll end up is this is a modification request. Okay? This is going to say, let's use the helicopter rather than the truck. That's the plausible interpretation in context. So this comes out as a modifying a solution using a helicopter instead of a truck. Okay, so if we have exactly the same situation, but I'd make one little edit to the utterance, and now change the city, right? So, as far as any sentence structure or lexical probabilities or whatever, this is an identical sentence. The only thing different is we have a different city and we know different things about it. In this case, the reasoning is, well, there's no plan to get the people at Barnacle yet, so this is a reasonable new goal. And so the conclusion is it's a request to introduce a goal to evacuate the people at Barnacle by helicopter. Okay? So we've got essentially virtually the same sentence there, but based on what we know and what the situation is, we get radically different interpretations of how it's supposed to be interpreted. Okay. So, let's see, the problems. We'll move, I'm going to go on. Basically, TRIPS is very domain-specific. We built it to do that task, which was, and it had limited ability to shift topics, and it didn't have very much initiative, that mixed initiative. It was mainly driven by the user. So the second system I want to show you is we move ahead 10 years now. So we're now 10 years ago. And this one we're looking at a system situated in the world of the web browser, okay? Web browser, you can perceive a web browser, you can perform actions in a web browser. It's like a physical world that you can live in. Many people do these days. So the plow system actually learned you could teach it new tasks using a dialogue. And it could actually do one-shot learning of fairly complex tasks by combining both observation from the web and the language, of course. So it's a collaborative agent. It can do execution, it can do task learning, and it can update its knowledge and about tasks and what it can do. Okay? So let's just look at this here. I'm going to speed up a little or I'll run out of time. So in Plow, we have explicitly, this is the first time we explicitly have a model of problem-solving driving process. The other one, it was kind of implicit in the way we built the system. But in Plow, it's explicit there. And here's an example of how the two-level model would work with just execution, right? Let's say the user says, let's buy a computer. Well, this is, you can see there's a whole set of kind of collaborative problem-solving tasks up there. One of them is execute a plan, and one of the things you do first thing you do in execute a plan is identify what the task is that you're doing. And in this case, we identified that it's purchase a computer. Okay, so we've done on this proposed goal, we've understood what the problem-solving action is and what the domain action is, and we know this task. The system might come up and say, okay, what is the budget? So at this stage, we're executing this plan, and we look at what do we need to know, and we get that we need to know a budget in order to purchase a computer, so we ask a user for it. So that's a simple little bit of task execution. So in task learning, we've got the collaboration level, but there's nothing at domain level yet. And they say, let me teach you how to buy a computer. Okay, so that is, we recognize that that's going to be a learning task that we're starting, a collaborative learning, and we're identifying a task again, the same step that was in the execute one, and it's purchase a computer. So we add purchase a computer in as a new task. We don't know anything else about it right now. And then they say, first we identify the budget. Okay, so there we have learning a step of the plan, and we add a step to the plan down below. Okay, so you can see at the task level, domain level here, the tasks are kind of identical. In one case, we're building it. In the other place, we're executing it. And the difference is what's happening at the collaborative problem-solving level, collaboration level. Okay, so let me show you again a 1 minute, a very, very simple task that you can train with Plow.
Let me show you how to find restaurants near an address.
All right.
Go to this web page.
So the system's watching
Show me.
everything that's happening in the web browser there.
All right.
Put restaurants in the place name field.
Okay.
The street address goes here.
Okay.
The city goes here.
This is a bit boring here, but it'll get interesting in a minute.
All right.
And the state goes here.
Okay.
Click the search button.
You can see up in the upper
Okay.
right-hand corner that's the procedure being built.
Here's the list of restaurants.
So at this stage, it's using its knowledge of searches and a set of search results. It gets a set of results. It can
Can
break
you
them
check
up,
that I understand the information?
parse them.
This is the name of the restaurant.
So the system learns from its one example and can apply it to all the others. Of
Okay.
course, this is a perfect dialogue. If there were mistakes, there'd be a lot more complicated interaction. But that takes longer.
This is the distance.
All right.
Keep the restaurants closer than 1 mile.
Okay.
All right.
I'm finished with the demonstration.
So there's a demonstration.
Okay.
Let's practice.
So now we're going to execute it.
What is the state, the address, and the city?
So it's figured out what the input parameters are.
Okay.
And now it's executing. You can see up in the upper right-hand corner, and you can see it's driving a web browser.
I am finished.
And we have the task done. Okay. So as I said, it's just about one of the most simplest tasks you could probably teach it. There are much more complex tasks involving you can iterate over results and go to other web pages and do other things like that. But they take much longer to describe. But anyway, so this system again is doing it's basically going through doing problem solving and learning as it goes along. There's a lot of information about how it combines what it observes in the web page and the language in order to get the one-shot learning on what goes on. Very quickly, because I do want to get on to the rest of it, this one was pretty rigorously evaluated with human subjects, and this is part of the Keynote project, the DARPA-funded project. There were 4 task learning systems here. We were the only one that integrated language and observation. But we had a set of subjects coming in. They were trained on all the systems. They then got 10 new tasks, and they had to go through and define as many of those as they could using whatever systems they wished. And then once they had these learned task models, there were inputs that went through, and they ran these through the system, and then they scored how well the system did. So you get partial credit. For instance, say you needed to know when a concert started, you get partial credit at least for getting to the web page where that information was, even if you didn't get the information off it, for instance. So there's partial credit. In the evaluation, so with the 4 systems, Plow was by far the most preferred system. 55% of the tasks that were completed were done with the system. It was used successfully by the most number of subjects, and it received the highest grade per task. So it actually performed relatively robustly in some concrete tests. But let's move on quickly to the present. So now, what we've been doing in the last 5 years is saying, well, these other systems were great, but every time we go to a new system, it's a huge engineering effort to build these things. So how far can we go towards domain generic technology for collaborative problem solving that you can just reuse with any system you want? And this is sort of how this system looks now. So the goal is to produce as much reusable processing. All the green is what we're doing generically now. Okay, so you just you just plug that into the next system that you have. What I think is always going to be domain specific, of course, is the problem solving for that particular domain, because that requires specialized knowledge, specialized reasoning techniques. So the purple is what you have to define to build a new dialogue system. But that's still way simpler than trying to build language models, dialogue models, all the interpretation, all the other things. So the current thing we're doing is we're building a single system that supports many different problem-solving domains. And we have 4 of them. Actually, there's 5 or 6, but I've got 4 here that we're using. And in these systems, we're using exactly the same language understanding, discourse interpretation, and collaborative problem solving. Okay, the first one is Blocks World. And this is in collaboration with companies SIFT and SRI. In this one, the system and the user are, this is a physical blocks world there. It's got cameras with Kinects for perception, and it has a little agent avatar coming back. The system and the user are both given goals to achieve, and they must coordinate their activities to achieve both goals under differing constraints. And some of those goals cannot be achieved unless they actually agree to share resources, like a block. They've got to use the same block in 2 different structures or something. And additionally, the system can learn new object definitions, say what a tower is. If a user says, I need to build a tower, the system might say, well, what's that? And can learn from dialogue interactions and demonstration. So that's one world, Blocks World. The next world is biocuration. This is a dialogue system. The main collaborator is the Harvard Medical School Assistance Biology Group. And here the user presents a problem that requires building and running a causal model of protein pathways. Okay? The system has access to vast biological resources. There's an immense amount of biological resources out there, ontologies, pathway commons, and many other things. And both user and system may propose additions. And then they can actually, once you build these system models, you can actually simulate them using the tools that Harvard has. Okay, they have several different ways of simulating causal models. And so that's the second domain. Looks pretty different from the first domain, you might say. Okay, then even more different. The third one, this is with the University of Arizona. This is music composition. Okay, the system and the user collaborate to create novel musical compositions. That's the goal. Currently, the system allows fairly simple editing from natural language on musical things. So you can say, I don't know, let's see, you can say invert the notes. That's the third one down. Invert the notes in measure 2 around G4. And it'll convert and do that. So that's music composition. The last one, which is the newest project, and the one I'm most excited about now, is world modeling. And this is the user helps a person model and analyze complex scenarios involving agriculture, climate, personal economics, trade, and the first kind of issues we're looking at are food and security issues. Are people going to have enough food to eat in South Sudan, for instance, in the next 3 years? This requires a large range of capabilities, including reading and acquiring data from the literature, planning how to combine suites of existing simulation engines that have been built. There's quite a few out there. Explicit discussion of underlying assumptions and trade-offs. These all require a lot of assumptions and trade-offs. And then you get results of like a probability distribution over so what's it going to be like in South Sudan, food insecurity over the next 5 years? Well, depending on what the weather's going to be like and some of these other factors, you end up with some sort of distribution of how many people, say, are going to go without adequate food. And then you can change some assumptions, and you can see a different one. Okay, so the challenge is in supporting all of these domains with a single system, except for, of course, the back-end reasoning, is first the semantic parsing. Are we really going to be able to parse all of these different domains with the same system? And the answer is yes. We've done that part fairly successfully. Generic management of collaborative problem solving. Can we really build a system that manages all these dialogues through and does all the complexity? It certainly looks like we can do that. We're in the middle of building that. And then the last thing is, well, okay, now you've got the generic technology. We still have to build a significant thing on the back end that does the domain-specific stuff. How hard is it to integrate? So those are the three things I'm going to finish up the rest of the talk in. Okay, so semantic parsing. If you look at the literature, most semantic parsers that are broad coverage are actually very superficial. They're mainly doing predicate argument structure, and you get the words or something like that. No semantics or ontology or anything. But they're primarily syntactic parsers with a little transformation on it. On the other hand, deep semantic parsers that go down to, say, a database query language or controlling a robot commands or something that has a deeper semantics in a domain are inevitably narrow. They're generally done with training on a bunch of data, and you learn a system, say, for a particular robot, and you couldn't even use that on a different robot. It'd be completely, you'd have to start all over again or whatever. Okay, so the challenge is, can we achieve broad and deep parsing? And I'd say we are relatively successful at that. This is the TRIPS parser. It can parse, it's a generic parsing system for English. It's ontology driven. It's driven by knowledge. And it builds complex meaning representations, which I'll show you in a sec. But let's see, it's driven by a 4,000 plus concept ontology that provides a semantic scaffold for the meaning representation and drives disambiguation. It has over 100,000 word semantic lexicon, of which 10,000 was hand-built. The rest is automatically derived from WordNet, bootstrapping off the hand-built entries. Extensive grammar of English, mainly adopting ideas from HBSG on the grammatical side and construction grammar on combining semantics and syntax in grammatical rules. Parsing is best first search with weights mainly affected by the semantic preferences encoded in the ontology. That's what I mean by ontology driven. So, and accepts advice from a wide range of preprocessors. You can try this online there. There's about 7 different versions of the parser with different search parameter tunings for different domains and different their named entity recognizers and things like that. And it's also, in fact, most of our collaborators use the parser by web services. So they send sentences or paragraphs or even papers over, and it sends back parsed input. In order to make this all work, you have the core parser in the middle, but we do a lot of pre-processing. In particular, named entity recognition is going to be different for each domain. So if you're building a domain, you need to do a named entity recognizer. In most domains, not all. The blocks world doesn't need pretty much anything. Biology needs massive, like millions of named entities. Part of speech tagging and sentence bracketing done by statistical parsers. All of that could be advice coming into the semantic parser. And at the other side out, we have ontology mapping that then takes the generic logical form and transforms it into the representation that the back-end reasoners need. Okay, so just 2 slides on what this representation looks like. Here is a very simple thing. A dog saw the pizza. This is an excerpt of it. You see the C is an event there with 2 roles, the experiencer role and a neutral role, where we have a dog and a pizza. The critical thing here is these nodes are actually all part of an ontology that's used to drive the reasoning. So we know that seeing is an active perception, which is a form of perception verb, which is a form of event of experience, which is a form of event of state, and it keeps going up from there. Dogs are mammals or animals or organisms, natural objects. Okay, so then there's a lot of detail in the ontology. Just quickly, there's a speech act that's identified from the, at least on the surface form. Main predicates, arguments as semantic roles, full embedding of other predicates in there, tense and modality, implicit arguments. Note that that person, the pronoun I there, is actually the subject of the want event, the try event, and the consume event. Whoops, I don't know why that didn't come up. And in fact, formally, this is the representation here is if you have anyone's been looking at constraint-based underspecified representations, this is subsumes some well-known theories such as whole semantics and minimal recursion semantics. And there's a paper in computational linguistics coming out doing that. The generic problem-solving model. So here's the generic, so that was the parsing. Sorry, it was a quick transition. I'm trying to speed up. So here's the collaborative problem-solving model in a nugget. We have all our domain-specific reasoning that I talked about. That connects to private system reasoning, connects to modeling collaboration, which connects to communication. And so basically, these are components that come out in order to get the right interpretation. So just looking at the collaborative problem-solving model, we actually formally use it. We have problem-solving objects. These are objects in our planning system, which are goals, actions, steps, problems, obstacles, resources, current situation. We have operators, such as adopt. You can adopt a goal. You can abandon a goal. You can defer a goal. You can identify a problem. And then we have the speech acts. You can propose things, accept things, reject things, answer things. So let's plan my travel for today is a propose of an adopt of a goal. Okay, so you kind of compositionally can kind of pull out from these three dimensions what it is. So that's sort of the collaborative problem-solving language. The dialogue is driven by a transducer problem-solving agent that looks a bit like this, and I'll show some examples that you can actually read in a minute. But basically, this transducer is mapping between inputs coming in, which, say, is some parsed input from a user, and it transduces it into a message to the domain-specific problem-solving system. Or the domain-solving problem system sends in a message. It transduces that into, say, an output to the user. That would be the simplest kind of interaction. So it's managing the message flow between all the language interpretation and all the domain-specific reasoning. So here's a really simplified version of what it might look like. So here's an initial start state, which is proposing an act. And there's an input pattern, say, from a parser that says, if I get a propose or a request act of something where it's an event of action, then I'm going to request to the behavioral agent that evaluate whether proposing, say, adopting this as a sub-goal is a reasonable goal. Okay, and there's other transitions there. This is just one example, one possible, okay. And then the reply might come back and say, yes, that is an acceptable problem-solving act to adopt the goal. And so then it might, this transition here says, okay, now we're going to commit that, and we're going to acknowledge back to the user, and now we have an established goal. Okay. So basically, going through this network here, there's sort of happy paths. They kind of, you can think of the network as going from beginning to end as sort of grounding a single discourse unit of where we end up agreeing on something. So you might go through this network where you say something, identify a plausible action, ask to evaluate, and if it approves, commit to a goal. That's sort of what we just saw going through the network. So that's a happy path, we call that. And there's many proposals and just direct extensions. Then there are sort of minor bumps in figuring out what's going on. Here the user, say, proposes an action. The system doesn't understand exactly what, but has a guess. It might clarify the guess with the user. And if the user agrees, then the system now knows what the goal is and what that action was. And here's an example from a blocks world. The user says, put a block on the table. The system can't quite figure out what we're trying to do right now, and it says, are you trying to build something? And the user says, yes, I'm building a tower. And the system says, OK, and now it knows the goal is building a tower, and it puts a block on the table as part of that plan. OK? So again, this is the finite state transducer just handles enough dialogue until we get to a point where we're done on this transaction. and then it starts again. Okay. So just getting ready to go through the last few slides here. This is kind of a summary of all the different things. On the left here are all the different things you can do generically. Parsing, interpretation, reference resolution, a collaborative problem-solving agent, intention recognition using a library. And then this is the things that you need to provide. So let's just look quickly about if you had a new domain, what do you have to do? So this is the crucial part. This is you know, is this technology, can you really bring up a new domain very quickly? Okay, so the first thing you have to do, well, if you have a domain, you have to have your reasoning engines, right? And presumably, you've got an ontology of what it uses, and you have all that you have to build in order to build a system. So what you need to do is first define named entities. So for instance, ROS is a protein in biology. C is a note in music. And depending on the domain, we have a lot of named entities or not. I already mentioned that. And then, besides the named entities, we may have to define, and this is generally not very many, but we might have to define a few domain-specific events and terms that do not have correlates in general English, okay? So, in biology, phosphorylation, right, is talked about a lot. But it's not really a common English word, right? It's a biology word. It's not in the lexicon. So we need to know what phosphorylation is, and we add it. It's not in WordNet. So that's a word that you would have to define for biology. And we had maybe 50 of these terms that you need to define for biology. On the other hand, transpose does have a very specific music interpretation, but it also is a typical word of English. And so that's fine. We can parse it in its generic sense, and then it can get transposed into the musical sense. So transpose doesn't have to be added. Okay. The second step is linking these ontologies, and we have a graphical tool to do that, or you can write a set of rules to transform it. But essentially allows us to say this generic sense of the word maps to this specific thing in our domain. So you might have step in the blocks world might map to some object with some physical object in the blocks world, right? So whatever that might be in the ontology used by the blocks world. In music, it's a unit on a pitch scale. Okay, and so both of these can be, the different interpretations will get done by this mapping based on the domain you're in. In move in the blocks world's physical motion. In music, it's changing notes. Okay. Step 3, the big one, of course, you have to define your reasoning system and the kind of a kind of skeletal plan library if you want the system to do some essentially quick intention recognition in order to find out whether something's likely to be, whether this thing could be a sub-goal of another thing or things like that. Okay, the status. We're like 2 years into the blocks world. We've got dialogues for mixed initiative construction of objects, where you give the user a picture of something to construct, and it can interact back and forth and build it. And the system can learn new objects from language definitions and demonstrations. Biocuration, we're also 2 years in, and we can build and simulate simple causal models of proteins. Musica, we're about 1 year in. We can edit simple scores. World modelers, we're just getting started on our first example, which is what happens to the crop yield if we cut the fertilizer in half. We're trying to answer that question, and it requires a lot of work. Okay, so the take-home message. It seems likely from our experiments now that you can actually define these generic parsing and dialogue management in a domain-independent way and reuse them for these different domains. With the ontology-driven system, adding new capabilities requires relatively minimal extensions to the language and dialogue system to make them work. And the final thing is let's stretch ourselves a little bit. Let's just not look at filling in frame slots and think that's the end of the world for dialogue. And okay, that's it. Thank you very much.
Okay. Thanks a lot for a really great talk.
Thank you.
I think we have time for some questions. So raise your hand if you have a question, and we have our people come with a microphone.
How does it scale across languages?
Sorry, I can't quite. What was
How
that?
does it scale across languages? I mean, you've done basically with English, right? What happens?
Right.
Can you just do transfer learning across languages?
That's right. That is the major weakness of this is that at least on the parsing side, we only have English, and that was a significant hand-engineered work. So there is no simple transfer on the parsing yet. I think a lot of the ontology work and the concepts of it are general and would apply to other languages, but there's no simple way to do it, and there's actually, given the complexity of the semantic representations, it's not something that's very amenable to, say, annotating a very large corpora to learn another language. So that remains a significant issue. My belief is that all the dialogue work is universal across the languages. And so I don't think conversation works differently, and I mean there may be different social conventions and things so there's tweaking, but the overall process of conversation doesn't differ between cultures. But you're absolutely right. The big weakness here of why can't we just use this for everything is we only do English.
I have a question here.
Yes.
Here.
I can't see you.
Okay, here.
Well, anyway, just talk.
Right.
I can't see you, but it's okay. Oh, there you are. Okay.
So my question is most of the examples that we saw there, the human agent is the one who is driving the conversation.
Yes.
So what would it take us for us to move towards a more partnership kind of a conversation where the machine is also like suggesting alternatives or driving the conversation? Right.
Yeah, it's an excellent question. And in fact, that's the reason the blocks world stuff is defined the way it is, where actually both the system and user have goals, is to address that issue, that now the system has to take initiative and act in order for the problem to overall be solved, because only the system knows what its goal is and how it could satisfy it. But most of the other domains, yeah, it's they're and I think most of these applications are going to generally be at least human-initiated, although the kind of solutions in all of these domains, kind of what might be good solutions are things that the system might initiate back. But ultimately, the goals, most of the time, will come, in most domains, I think, from the user. So it's not going to be fully kind of symmetric as we get in the human-human conversation a lot.
So, do we have any questions from A2 that we have on video feed? Raise your hand in that case. Okay. So I have a question. So, you're doing this situated physically as well. So, how do you model the actual visual part? What's actually happening? The actions of the user?
Yes, well, actually, most of that is we're not doing, right? We're just we have partners that are doing the work and stuff like that. The only physical domain we have is the blocks world, and that is we are depending very strongly on the Microsoft Connects, and there's 2 of them, and they very accurately locate objects in the world. And then we have color detection. We have all sorts of different feature detections on these objects. And then the more complex structures are like what a tower is or something like that, are represented as sets of constraints of how a set of objects such that each one is on top of each other or something, or they're vertical, and there are various different physical constraints on defining what these complex objects are.
So would you imagine you could also learn how to cook food?
To cook?
Yeah.
Well, we could learn. Oh, you mean yes, right? We don't
By
have
demonstration.
Right, right. By demonstration, right. But what we'd learn there, at least for what we have, we would learn there more what the recipe was and things like that. And we did have one project where we both were learning what the recipe was and also how to recognize the actions when a person was doing it. The idea there was, this was a sort of an aging in place type thing, that if you could learn the everyday routines that a person does, say, in the kitchen, then if you can watch them, you could help them if they get confused in the middle. So we did a little bit of work on that. I wouldn't say we had great success. It's a very difficult problem.
So any other questions? Otherwise, yeah, there.
Well, you showed very impressive systems.
Thank you.
And it looks like it's a staggering amount of work.
Yes.
And there are many, many components. So my question is there any view in the future where some of these things could be standardized and you can use building blocks from different places to come up with something that might collaboratively be improved?
Yes. Yeah, now that is always a challenge. And I think on the parsing, we actually have made pretty good progress on that now, although it could certainly still be improved. But now, as I mentioned, most of those collaborations, people are actually, all they're using is web services, right? They send over sentences and which kind of domain it is, and it gets back the parsers. And so that's pretty lightweight as far as, and very easy to use, and that's how most people are using the system. Although you can get it for download and do it, that's the hard way. But all the rest right now, we're hoping to ultimately get to that point with the other ones, but that's not there yet. And even with the parsing, if someone had a new domain, it's one of those things where we could help them, maybe in even just a day or something like that, set up a parser that'll work well in their domain, because you need to set kind of search parameters. So very different, for instance, whether you're parsing text messages versus biological papers, right? The language is very different, the sentence lengths are different, and all those other things. So there's a set of search parameters that you set in the parser in order to make it perform well in the kind of genre it's working on. And that's rather complicated and actually takes a little bit of experimentation. But that's kind of the thing. We probably still need about a day's work to tailor something to a particular domain. But otherwise, after that, you can actually just send it off and parse. But
yes.
The rest of the system still remains much more of a complex thing that I fear to give to people to try and use on their own.
Okay, I think it's time for coffee, so let's thank the speaker again.
Thank you very much.